Yes, so good afternoon, everybody. So apologize for people who attend to the OME conference because this is the same presentation I presented 2 weeks ago. It's very fresh. But yeah, here the idea is just to insist on the way to be representative when we want to characterize the biofouling. So more focus on the site characterization phase than inspection during in-service life. And yeah, in the first discussion we had during ABIOP project specifically, we identified with our industrial partners and academics also that biofouling is primarily an issue on mooring lines and dynamic cables. So then the question raised was how can we be really representative and more accurate on the colonization of such component? And therefore, the question about the influence of the material, but also geometry. So we will discuss this and then assess how we can analyze and extract from these measurements of a live species parameters which are usable for design modeling. And this is the reason why the paper was titled Strengths of the Multidisciplinary Approach to Enhance Biofouling Characterization from Comprehensive Requirements of Engineering and Environmental Analysis. Here the idea is to start from the real need at the end and adapt the way of measurements. So yeah, it was presented at the OME. I just mentioned this. A very brief. I will start with a very brief summary of the state of the art, but as Elena mentioned, you can have more detail about that in the recent publication we have during the project. So the review on biofouling and the reference are here and other slides. So yes, and then we will see the first experiment we perform to assess representative condition and then analyze first results and conclude on the recommendation to provide better representative characterization. So yeah, for the brief state of the art. So just keep in mind that the biofouling was introduced in the recommendation for certification body, firstly in 1999 by NORSOC, in identifying that it may have an impact on the hydrodynamics loadings, the additional weight, and but also potentially on the structural instability depending on the object. And then progressively, it's not automatically in the correct order, but all the certification body are in line, introduce these needs with sometimes some specificity depending on the certification body. For example, Bureau Veritas insists on the fact to introduce this in the fatigue analysis. Introduced also the fact that we can characterize it thanks to thickness measurement and biofouling density, equivalent density. We'll talk about that. So it's the same for the other one. Here I make a focus just on the specificity between each other, but globally they are full in line on the way to do it. So ISO and API have some specific recommendation for inspection. Typically, they introduce the fact that thickness can be measured using a T-tape, flexible T-tape. Also, how to define roughness with certain assumptions. And also, DNV proposes some improved formula to introduce coefficient, hydrodynamic coefficient, taking into account biofouling. And then some first default values, if we don't have any in-situ data, are proposed. So I think that all of you know these recommendation values, the famous maximum thickness of 100 millimeters and a constant biofouling density. But this is typical of North Sea, and it's quite difficult to use it everywhere in the world. So here, now, to date, the modeling assumptions and the way to calculate, to make some calculation by modeling the biofouling is quite well described. But the question here, and this is the philosophy of our investigation, is how can we characterize a live species to provide these equivalent parameters which are required for calculation. So yeah, in the first experiment, we performed this at Ethel site. We systematically deployed some different materials, different diameter, different lengths, and also different shapes. So plate, but also cylinder, to assess if there is an influence. The fact that we use cylinders, so rope and tube, obliged to develop some specific measurement tools. So it was something exotic, I mean. Yeah, so we deployed in terms of materials, so polyester, polyamide, an hybrid between polyamide and polyethylene, polyethylene plate, PVC plate, steel, and HDPE, which is high density polyethylene, which is representative of external layer of dynamic cable. For 18 months, so with colonized sample, but also limited in time regarding the long-term application we want to be representative of. So from these experiments, first of all, we will speak about the engineering conclusion. So I mean by engineering conclusion, focus mainly on the data that are used in engineering model. So typically thickness, white in air, white in water, density, and displaced volume. So if we have a look on this data, we didn't observe a real clear trend of the material, not of the material, sorry, but of the diameter. So we don't have a clear influence of diameter. The lowest was 14 millimeters, and the highest was 120 millimeters of diameter, I think. Nor the length of the sample, and we only observe a difference between the geometry itself, so plates and cylinder. Here we have some difference for the same area of colonized sample. And we attribute this mainly because plate samples have a specific orientation, which could influence all the transports of larvae, nutrient, but also the light and also current. So this is the main point we observe, but no clear difference also among the different materials. So here, the first question is raised: are we representative with just 18 months of colonization, meaning that we want to be representative of 25 years. But if we stopped here, okay, we perform engineering analysis for engineering purposes. But even in that objectives, if we had the taxonomic approach, we observe some more detailed trend. And typically, what you can see on the screen is in the blue circle, you have all the different cylinders with different materials, so nylon, polyester, and hybrid. And the HDP in green circle, and you can see that on here, this is the cover of the dominant species in percentage. And you can see that the community seems to be similar between different fiber ropes, but different on the HDPU tube. And this is something very important because we have a limited time observation, but from this, we can expect that the stabilized state will be slightly different between both set of materials. But also, we can see also that on PVC, we have a different community distribution also. And knowing that a lot of experiments have been done with PVC, sanded PVC, now our recommendation perhaps is to stop to use PVC because we don't have any component in PVC on floating offshore wind component. So that's the first experiment. From this, we deployed systematically on different sites these samples. So systematically, one of the families of fiber rope, it was polyester, and also in parallel, one HDPE tubes in different numbers of samples. And for this is the objective of BIODHYL, so I will not insist about that, but we have a focus on the area, the fine spatial scale influence, and also the water depth influence. But today, again, we are mainly focused on the protocol of measurement. So don't be surprised in the rest of the other part of the presentation. Perhaps in particular on density, you can have some slightly different values. This is because here the purpose of the exercise is to be representative in terms of protocol. So I gathered a maximum of data to be statistically representative and in mixing different water depth and area, etc., for the sake of the exercise. So the first lesson from this experiment is that coming from plate samples to cylinder samples involves more complexity in terms of supporting structure, which are significantly heavier, but also more complex. And that's the same for the measurements. So just keep in mind that if you want to go on such experiments, it's more complex, and don't neglect the design part. Well, this is just an engineering lesson, but important to share with you, I think, because we have to improve the supporting structure, etc. Here, I think we are on the most important point I want to share with you from these experiments is the fact that we really need to be representative of the alive species, so meaning that we have to take into account only measurements when they are in their natural environment. Typically, here, this is an example of bivalves of mussels, which are working as usual and feeding in filtering the water. So you can see that in the natural environment in the sea, they are all open. But when you perform the measurement in our protocol, we have just 10 seconds of drying for the mass in air measurement to minimize this effect. You can see that instantaneously all the specimens are closed with a mandatory amount of water which have been released. So we will see that all of this have a huge impact. So also in the publication, we speak about that in analyzing what we need to represent in terms of physics in the model, and in front of that, what are the behavior of species and the issue we can have. So typically, we have some interstitial water and trapped water in different specimens. We have just speak about this here. Also, a real issue to define the roughness, because thickness is used to derive volume, but also roughness. Why? Because it will impact the external flow. So we have to really account for the final objective to define the best way to provide these measurements. And inherently, you have also a porosity effect, which will impact a lot your volume and then the mass deduced from this. So don't forget all these specificities and the fact that we have some large species. So here, this is the main important message we want to share with you on that aspect on density, because we are always assuming a constant, unique single density value, which is an equivalent properties of different species and community. And the way we are measuring it will impact a lot the value and therefore the mass you can extract from this. So typically here, what you have is in red, you have the density which have been calculated using the mass in air and the displaced volume, so the real volume of the biofouling. In blue, you have the density which have been calculated using the mass in water on the real displaced volume. And in yellow, we are more close to the usual practice. This is the mass in air which have been used, and also the volume deduced from the thickness, so as recommended. And in blue, the mass in water using the volume deduced from thickness. And you can see that when we are using the volume deduced from thickness, we generally underestimate the density. Why? Because the volume is highly overestimated. Since we divide it by this volume, at the end, the density is underestimated. When we use the mass in air, so red curves and yellow curves, you can see also that the discrepancy is significantly higher. And this is because this is related to what had just been mentioned before, the fact that in air, the species released a mandatory amount of water, and there is a lot of discrepancies because between the different measurements, different samples. So by the end, we strongly recommend to use only the mass in water measurements to deduce a density, and ideally also to associate the displaced volume, which is significantly more representative than volume deduced from thickness, so if it's available. Also, you can notice something, even if we use these measurements, so the dark blue curves, you can see also that there is always in the transition phase some variation, natural variation, but after 2 years, it seems that the density and potentially the community distribution is more stable. So this is also a recommendation to not provide values younger than 2 years because there is a lot of variability. So I think I have to accelerate, perhaps. No. Okay, but
it's
this
okay.
is
You have a bit of time still. So
okay. So here, this is now a comparison between the values we measured using the methodology I've just presented, so with displaced volume and mass in water. So this is our values of reference, and we compare to the ratio with the values using the recommended practice to date, meaning we derive a volume from the thickness measurements, and then we used the density which is recommended, so the unique density, which is about 1,325 kilo per cubic meters. And we can see that generally, in using the standard recommended practice, we overestimate both mass in air, mass in water. Mass in air is in red, mass in water in blue. So this overestimation is very important at the beginning, but this is also due to the fact that when we have a small amount of BIODHYL, error and accuracy the error is higher of measurement. But and again, after 2 years, we can see that the values are more stabilized. And also that, but we still have an overestimation ranking between 1.5 and 2 in using standard recommended practice. So something interesting to keep in mind. So, and you can see here that we included samples age up to more than 4 years, so it becomes more representative for long-term application. I think it's the most important point on that. And then, yes, I just said that. Also, again, we try to have a look on the porosity rate, so which is defined just at the bottom of the slide. Here, the idea is to bring some statistics on the porosity in hoping that we will be able in the future to, depending on the community distribution, typical of the site, to be able to propose a porosity rate which can improves the values we can have from thickness measurement, because we are also aware that this is the most easier way to measure on site, and it's very difficult to provide. We need to scrap all the biofouling to have some fine data, and it's quite heavy. We can speak about that in the question sessions if you want, but so yeah, the idea is to assess the porosity rate. So you can see that the porosity varies a lot. It's not an easy exercise, so we have to still feed the database to see if we can reach some stability. But anyway, we see also that the porosity is very important at the beginning, and seems to be more lower and around 30% after 3 to 4 years. So some things to be confirmed, but it could be interesting to go further on this. Yes, and in the idea also, the porosity may feed some data to derive some more representative thickness also. So here's the main final recommendation from these experiments. We, from this observation, recommend to systematically, in the frame of characterization for floating wind, to deploy systematically in parallel fiber ropes and HDBU tube, not cable, because it's very heavy and we are just focused on the external layer, which is prone to be colonized. Also, if you make some measurements, use to derive a density for calculation, please use the mass in water, because it's really the only way to be representative. And if it's possible, the displaced volume, if you have the data. And also, yes, I speak about this a few times, but use only samples older than 2 years, or a minimum 2 years of colonization. And also, for sure, if you use multidisciplinary approach, for sure, you will be significantly more accurate in your data, and therefore in your anticipation prediction using simulation. And also, last point, we believe that it will be, because up to now, progressively there is some improvement in the methodology which are used, but today we speak very often about hard and soft fouling, and we believe that it will be also very interesting to imagine 4 different groups of hydromechanical perspective. So yes, soft and hard, we mixed the white effect, density effect, and the flexibility effect. And for sure, in terms of hydrodynamics, these have different impact. And if you want to increase the database we use for hydrodynamic, we need to perform some new basin tests, which is more representative. So it will be very useful to build database around these four group of species we have in mind. So in separate each time the white and the flexibility. So mixing light and heavy and flexible stiff, because then we will be able to provide more representative hydrodynamic test. So yes, I think it's all I want to share. Yeah, to share with you.